We're going to talk about flowcharts. We said, yeah, they're not the best things for real-time systems, but again, they're familiar and they are useful. And so, all of these methods, they have some basic syntax. And so flowcharts, an oval is either the stop or start indicator. A rectangular box is an execution. Arrows are the flow of program execution, and the diamonds indicate an if-then or a conditional branch, right? And so we're going to see this as either a yes-no kind of answer. And so an example now of the Roomba. So this is a flowchart that goes along with this description, okay? Now, so you can see what happens is when at the start of the program, it sits here and it waits to see if the button clean was pressed. If it's not, it's just going to sit here, right? And it's going to keep testing, waiting for that button to be pressed. When someone presses the clean button, then the first thing it does is it turns on the suction motor, it loads up the spiral trajectory, and then it executes that trajectory. Okay, and we can see here that the basic loop here is going to be, it's executing the spiral trajectory, it's going to look for a bump sensor. If there's no bump sensor and no cliff sensor, yep, it's just going to keep executing the trajectory, look for the bump sensor, look for the cliff sensor again, round and round and round. Now, these other sections colored slightly different. So we've got the blue section, which deals with the bump sensors, and then the green section deals with the cliff sensors. If, as we're doing this execution of the trajectory, we do get a bump, okay, all we do is check. Is it the left? If it is the left bumper, remember we rotate opposite to where we hit. So if it's the left bumper, we rotate right. And we look for the peak signal as we're rotating. If it's not the peak, we keep rotating. Eventually, if we do hit the peak, then we are going to go load up the straight trajectory and head on to back to execute now the straight trajectory. And so that's going to do the same thing. It's going to start moving in a straight line. It's going to look for the bump sensor. It's going to look for the cliff sensor. And again, keep looping here. And again, if we get left, if it's not the left bumper, then it must be the right bumper. And so if it's the right bumper, we're going to rotate left, again, away from the bump, do the same thing. Have we detected the peak? No, keep going, keep rotating, keep doing, and eventually, okay, come back here to execute the trajectory. Now, technically, I do have a little bug here that there is a condition where it'll rotate up to 90 degrees to find the peak. So if it doesn't find the peak, it will just, if it doesn't find the peak, but if it is over 90 degrees, then again, it will load the straight trajectory and go back to execute. Now, the cliff sensors. What happens when it gets the cliff sensor? Again, it's executing a trajectory. It doesn't care if it's a spiral trajectory or if it's a straight trajectory. It's just executing it, checking the bumpers, checking the cliff. This is because this is the main loop. If the cliff sensor goes off, right? Remember, there are multiple cliff sensors, right? The first thing it's going to do, it's going to back up 1 centimeter because it immediately wants to get away from whatever it is. And all the cliff sensors, of course, are in front of the wheel, so we know that backing up is safe. So you back up, and then you ask, okay, are they both, do we have both forward and the edge sensor? Are they both triggered? If that's true, we're going to rotate 60 degrees, load the straight trajectory, and take off executing again. Now, if it's not both sensors, then it's going to check, is it the edge alone If it's yes, going to rotate 45 degrees. If it's not the edge, then that means it's only the forward sensor alone. So in that case, remember, it rotates 90 degrees. In both cases, you're going to load the straight trajectory and just start taking off in the straight direction, okay? And you start looping again. So basically this is the flow of execution of the program. Okay? Now, how do we represent that in a state transition diagram? And we've talked a little bit before about state transition diagrams. Here is the syntax. We didn't go into the full detail, but here's the syntax. States are represented as circles. Transitions are represented as arrows. The system must have a discrete set of states. And this is an example of a print spooler. There's a waiting state, there's a printing state, there's queuing, and again exit. We're going to talk, of course, about the Roomba and the states. And it's really important to first isolate what are the basic states of the software. What are the grand epics? The most important epics of how the thing operates. These are kind of equilibrium points of the system. And then the transitions are just those things that define changes in the state, right? They occur whenever some condition is met. And for us, we're going to look at actions that are taken during the transition, okay? And so, again, the system, when you're using this type of state transition diagram as an engineering mechanism, you have to think, does the system have important discrete states that I'm worried about? And then what are the events that cause the changes in the state? Now, formally, in state transition diagrams, there are actually two types of state transition diagrams. There's the Mealy and the Moore. And there's a famous paper that shows that, in fact, the Mealy STD and the Moore STD are actually the same. They can represent the same thing. It's just that the Mealy outputs happen during a transition, in the Moore outputs happen within a state. But you can pick whatever. We're going to use Mealy for our descriptions in this class, okay? And what we're going to do is our syntax is going to be, we're going to use one color for the transition, and then another color, in this case dark blue for the transition and light blue for the output, okay? And so you can see that the event that causes to move from print to the waiting state is the sent event, which says, yep, the job has been sent, and then the printer means the printer is now true, it means busy is now true, so the printer is busy, and then it goes into a waiting state, basically, and the print state is when it's getting it, actually doing a print, okay? Now, for the Roomba, however, remember we have this description of the Roomba, we have this description, documentation for the Roomba. What is the state transition diagram going to look like for the Roomba? Well, here it is. The basic states are of the program are, there's a waiting state when it's waiting for the button to be pressed. There is an execute state, execute the trajectory, that's when you're moving, and in this case it could be either a spiral or a straight trajectory. And then there are a couple of states that define how to respond to the various sensors. And in this case we have bump sensors and we have cliff sensors. And so there's a two-state subdiagram over here that represents the action required to respond to cliff events, cliff sensor events. And there's also a two-state representation of how to respond to bumper event, either, again, a left-right bumper event. Okay? And so here's what again, this is defining how the software operates. So at start, we go immediately into the waiting state. Now, often this has some initialization or whatever, but it's sitting there waiting, and it doesn't leave until the clean event happens. And the clean event is simply the owner presses the clean button. Now, and so that's the blue is the event. I'm sorry, the dark blue is the event, and the cyan, the light blue, are the outputs, which again happen during the transition for a mealy state machine. So we were waiting, we got the clean event, and so we're going to transition to execute, but we're going to make two outputs. We're going to turn on the suction motor, and we're going to set this trajectory to spiral. Okay, so it's going to sit here inside this next state, executing the trajectory, right? And it's going to be spiraling. Now, and so that's all it's going to do is sit there and spiral in this growing spiral as it closes around the room, and then bam, it runs into the wall. Okay, now as soon as you hit the wall, suppose that triggers the left bumper is the event that causes a transition from execute trajectory into, if it's the left bumper, we want to rotate right. Okay, so the left bumper is the event. We're into rotate right mode, so we start to rotate. Now remember, it's looking at a sensor while it's rotating. So this is still looping, and it's waiting to either see a peak, at which case it's going to stop rotating and move into the execute trajectory, and it sets as an output, if the peak event is detected, the trajectory gets set to straight. Remember, coming out of the wait state, the first thing it did was go to the spiral. Now it's going to the state, or straight state. So now it's going to be executing the trajectory again, but a little different trajectory. Instead of the spiral, it's now doing a straight trajectory. Now, I'm going to stop here for just a minute and point out that we could have separate the states. Instead of just an execute trajectory state, we could say that the spiral trajectory is an important state, and the straight trajectory is an important state. And then we could say wall following mode might be an important state. Avoiding the invisible fence, or going back to home to recharge. There are a number of possible states, and I felt for this, since there are only two trajectories, that really there's one state, and it's just executing a trajectory, and it's responding to air conditions, sensor conditions. It is perfectly legitimate to say, well, really, it waits, it does a spiral, and then it does a series of straight trajectories. That's also a valid way to think about it. That's going to require doubling, though. It's going to make a more complex state transition diagram, because now there's going to be a spiral trajectory which has the bump sensing on it, the bump and cliff sensing branches, and then it's going to transition into a straight line trajectory. And that, of course, is also going to have both the cliff cliff sensor response and the bump sensor response. Okay, and so you can imagine how that looks. And in fact, I could draw that out, and but just going to add a little bit more complexity. Okay, and it is up to you of what how you want to break down the important states of operation of the machine, and Some of that I will give you leeway on in grading. Some of the times, be careful of what the specification says, because there might be, this is a case where the natural language specification, for example, might highlight a reason for breaking it up one way or another.